maybe.
Okay, guys, this is the fourth lecture of Eyüp on Spin 7 geometry, and we can start now. Thank you very much.
Okay, thank you very much again for you and all attendants for coming to the last lecture about Spin 7 geometry. Again, maybe just I can mention we covered obtainions. Obtainions is the 8-dimensional geometry, and the calibration is the types of minimal theory of the manifolds, and we need the G structure, and we talked about the Spin 7 structure. Now we want to understand the Calabi-Yau manifolds, and before then that, we have to understand that the complex geometry just a little bit to be able to catch the idea behind the Spin 7. Here, the complex manifolds is the n-dimensional complex manifolds can be defined as the topological space with the charts that are homeomorphic to open sets of Cn. Actually, if you know that the classical n-dimensional, the real n-dimensional manifolds, you can define that at least two transition function, and this transition function has to be differentiable. At that situation, you can look at this map, and here the idea is exactly the same. For being a complex manifold, you have to take again the transition function, but you replaced Rn with the Cn. For each curve, you have to find that phi and psi, let's say, and for this transition function has to be holomorphic. So the holomorphic means for each map has to be depends on, I mean, at first you have to take transition function as the sense to Rn, but now we choose translate our function into holomorphic function. What does this mean? The holomorphic means you have to translate all information to Z and Z bar, okay? And XY turns out to be the Z and Z bar, but in the holomorphic case, everything is a function of Z, okay? Or you can enlarge your dimension, Z1, Z2, Zn, Z1 bar, Z1, 2 bar, and Zn bar, like this. If your function is holomorphic, everything has to be dependent on only Z1 to Zn, okay? So there's no Z bar cases. We can say that at that situation, the holomorphic function is defined with respect to only the Z function, not a Z bar there anywhere. So we can say that this is the complex manifold, and for these complex manifold can be defined almost complex structure. At least the almost complex structure is the starting point. We will construct on any manifold in a complex structure. Okay, the almost complex structure is like this. You have the J function, and this function is a structure actually, and you are taking the tangent bundle and the tensor to a dual tangent bundle. If you choose such J, and this J gives us an almost complex structure. And theoretically, actually, the J square is minus identity. Okay, so as a compared to the complex plane, actually, for I square equal to -1. So if you think about that n-dimensional objects, so you have to think about that the matrix algebra, and square has to be minus identity matrix actually, and so this is the generalization of this I square equal to -1 idea for here. If any spaces, any real manifolds has these kinds of J and this J square satisfy the minus identity, we can say that this real manifold has to be the almost complex structure, okay? And also, if this almost complex structure satisfy another situation, Nijmegen-House tensor equal to 0, we have to define the new types of tensor, and if it is equal to 0, we can say that this manifold is a complex manifold, okay? So almost complex structure is a little bit softer than the complex structure of a little bit distort the complex structure, complex manifold structure a little bit, but so to be able to be complex structure at the complex manifold, at first you have to be almost complex structure, and Nijmegen-House tensor has to be equal to 0. So any curve has to be integrable curve, and for taking the direction, the connection has to be 0 for all integrable curve. Okay, so almost complex structure is a softer, and you have to force the new requirement to be able to find the complex manifolds, and then but finding a complex manifold is harder than the finding almost complex structure. That's why we are starting with an almost complex structure, and for that manifold you can find the extra condition, and that's why we have to understand that the complex manifold and almost complex structure. So the Hermitian form is if you have almost complex structure and we have a matrix, so our matrix can be compatible with this the almost complex structure. Here you can write that if gxy is equal to gjx and jy, so jx is taking all elements to the orthogonal to x actually, and if you apply j to x and y, the metric doesn't change. So here we can say that at that situation G has to be the Hermitian, okay? And here if G you can switch J with the Jx minus sign, and from here you can define the two form, and this form is named by the Hermitian form because these two elements each two vectors, and this is the two form. And these two form spaces you can for the complex manifold you can translate the tangent bundle into the three parts. I mentioned that this part is the z bar, z element only induced from Z, and this part is the z bar. But if you look at that, this is dz bar here. Here only related with dz, this one related to dz bar, and this one dz bar. Okay, so here the important case for the real manifolds, the tangent bundle is very standard, but if you pass the complex structure, now everything related with the holomorphic parts, this is the holomorphic parts, and this is the anti-holomorphic parts. Okay, this is the composition, and here the lemma says that the Hermitian form induced from the metric gxy, gx Jy lies in dz bar, okay, d11 form, the combination of dz wedge dz bar, and this lemma can be checked somewhere. Lots of the complex analysis and the complex geometry book, and here the Kähler form is this one. If here we have the connection now, Levi-Civita connection on the real manifold directly, and for the complex manifold and the complex are almost complex structure J actually, here you can say that these the followings are equivalent. Taking the nabla v equal to 0 here for any arbitrary direction you can calculate, and it's gonna be 0, and this says that this is equal to, you can, J is also tensor, right? The element of here dz bar actually, if you look at that here, these elements dz and dz, I mean, if this one is the element of endomorphism of tangent bundle, you can translate this idea dz bar, and this information also equal to 0, or these two-dimensional form equal to 0. Both of them are directly equivalent to each other. And this equivalence, that if you have one of them, we can say that we are living in a Kähler manifold. So the Kähler manifold is the complex structure, but also we have to satisfy the one of them, either the Kähler, these two forms named by the Kähler form, by the way. This Kähler form has to be 0 or closed form, okay, or this J has to be 0. This one is the J, a parallel J structure, okay. You can preserve J on every direction. The idea of the 0 for all direction, you can preserve your two-dimensional form, or the closeness are equal to this condition for all direction. If you take the derivative of 2 form, you will find a 0, or if you take the nabla J has to be 0, means that for each direction you have to preserve that almost complex structure, and this named by the Kähler manifold. Okay, so to be able to understand that, or to notice that the Kähler manifold is the complex structure, but we have the extra condition. So for the Calabi-Yau manifolds is again the extra condition for the Kähler manifold. If you have again the previous lemma, the parallel structure of J, for the parallel structure of J, and if your complex manifolds, okay, so it can be said that directly the Kähler manifold we talked before, but for the extra condition, if you have a compact Kähler manifold, now we know that Kähler manifold is the more powerful than to the complex structure. Extra condition, what's that? The parallel almost complex structure, or the closed 1-1 form, or for each direction you can preserve your Kähler form. All of them is the same. If you choose the compact Kähler manifold with a two-dimensional object, you can say that M is the trivial canonical class, and this is the directly related with the trunk class actually, and or the first trunk class of a holomorphic vector bundle, the M10 is vanish, or your holonomy is SUN directly, it's reduced holonomy, or another equivalent, M can be Ricci flat. All of them are equivalent to each other, okay? And if one situation is satisfied, we can say that we are living in a Calabi-Yau manifold. So here we can put in some extra condition. If you have a complex structure okay, put n dv equal to 0, okay, we will find the Kähler form, Kähler manifold. And if Kähler manifolds put n Ricci flat or any of them, the holonomy SU2, SUN, okay, we can say that the Calabi-Yau manifold. And why this is important, we said that before it's directly interrelated to very nice geometric object, but at the same time, it's directly related to string theory, M theory, whatever. Okay, well, that's why it's very important for us. And for Calabi-Yau manifold, we mentioned about this one before. Here, the special submanifold induced from the calibration is induced from the holonomy, and if you define the calibration on these spaces, real of omega, and omega is the holomorphic volume form, this Calabi-Yau manifolds have the spatial types of the minimal submanifolds, and it's a minimal submanifold induced from calibration, and this calibration gives us the special Lagrangian submanifolds. Okay, and here, so for the Calabi-Yau manifold, we have to at first define the almost complex structure, the metric fixed, and now we have to define omega, and this omega is the holomorphic volume form. And here, if you take the real part of this omega is a calibration, and this real here, I mean, if you remember that for the calibration, if you look at that, the n, it's smaller than or equal to 1, and the real part of omega with respect to v equal to 1, we can say that this v or n, whatever, this v is the special Lagrangian manifold. Okay? Special Lagrangian submanifold. So these special Lagrangian submanifolds is extremely important in the string theory, and as an example, to be able to understand which one is calibration, how do we construct the theory, here the SU3 is a non-trivial example if you are living in a 6-dimensional manifold with an SU3 structure. Okay? So for each point, you can see that it's equal to R6 or the isomorphic to R6, but for here, if you have the Riemannian metric and orthogonal almost complex structure associated with the two forms, how do we determine these forms? Here, you have to define C plus and C minus, and for here, you can see that 3-0 form for this dimension, and so for C minus equal to J C plus, and the complex structure have a connection between these two forms, okay, 3-0 forms, and here you can see that if you have the 6th dimension, explicitly we can write that E1 I E2, okay, and E3 I E4 and E5 I E6, and you can multiply this one, okay, and this form gives us the if you take the real parts, okay, E1 multiply with E3 multiply with E5, and wedge product multiplying this part is actually the real parts, okay, real parts of omega. Think about that. This the bigger C, and this part is the real part, and you can check that the real part of omega is the smaller than or equal to 1 for each element, because length of this one is just a 1, and from here we can define at least one calibration, okay? And so here, these are the extra conditions, and C plus and C extra result actually. C plus and C minus gives us the omega cube, and this one is the non-degenerate form. So if you multiply with itself 3 times, it gives us the volume form actually. So this is the good relation for us. So from here, this is the Kähler form, 2 form actually, you can check. And so for this case, at least we see the non-trivial example. This is our omega actually, this is our 1-1 form. And you can see one element from the actually from the Z bar, the Z from another one induced from the Z bar. So you can construct N as the SU3 structure, and the elements of this one gives us the Calabi-Yau manifolds. Here, if you have the Calabi-Yau manifolds, from here we can continue some information about the mirror duality. So what does that mirror duality? We don't know yet, but at first we have to understand that some structure also. So which kind of structure? The symplectic structure. What's that? The symplectic structure is a 2-dimensional manifold also we have to define at first. So if you have a closed form, okay, and the form is the alternating, if you switch x and y, it has to be equal to minus sign, and non-degenerate, if we x equal to 0 for all y, x has to be 0, okay? There's no unusual element maybe, so it has to be equal to 0. So the submanifolds of the symplectic form, it's a special name. One of them is the isotopic submanifolds if you have an embedding, and if you restricted your form equal to if you restrict your form into N, you will find a 0, okay, directly, isotopic spaces. And as an example, for our 2N, the trivial one, E1, maybe X1, Y1, okay, X2, Y2, and Xn, Yn. These are the basis elements of our 2N, and you have to put an wedge product multiplication X1, and you can glue 2 spaces into each other, X1, Y1, X2, Y2, okay? If you calculate X1, Y1, they are orthogonal to each other. X1, X2 also orthogonal to each other. You can separate your 2 spaces into 2 pieces, X1, Y1, X2, Y2, okay, 2 separate pieces. And isotopic space is generated by X1, Y1, okay? And because the orthogonal complement contains itself X1, Y1, X2, Y2, X3, Y3, dot, 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 and this space is sitting inside of the orthogonal complement of itself. And from here, we can say that the isotopic submanifold, but the Lagrangian submanifold is, don't confuse spatial Lagrangian, okay? So we are just looking at the spatial Lagrangian defined on the Calabi-Yau manifolds, but here the Lagrangian submanifold is if you are 2-dimensional object, half of this dimension and this condition, actually the largest isotopic submanifold, actually Lagrangian is named by, dimension is the half of the real dimension, so it has to be n. And also, if you calculate the form on this Lagrangian, also has to be equal to 0, okay? From our spaces, from our simple example, x1 to xn gives us And the Lagrangian submanifold actually direct the largest dimension. Okay, and if the two submanifolds are transverse, this means that you didn't lose any dimension for the transaction. Here, this one and this one living inside of the two-dimensional object. If you look at that, you have two different directions. Okay? Not overlap this definition, not overlap this this transaction here. This one is one of them. This one is another them. But if you look at that, the another intersection, this one, and here other one. If you look at that, the intersection, this vector and another vector are overlap to each other, and for these cases out of the transverse intersection, okay, but this is not intersect transversely. So why this is important? Because if they are transverse intersect transversely, we can construct a new theory. It's named by the Floer homology. That's why we gave this one. We want to intersect transversely for the submanifold, and the theory of this intersection, the tangent plane of the first one and the tangent plane of the second one has to be equal to the tangent plane of the complete spaces, okay? But if you look at here, for this point, there's no transaction, there's no intersected transversely because we missed the one dimension in two-dimensional object, okay? And exact symplectic submanifold, exact symplectic manifold is if you define the omega equal to d alpha, we can say that it's exact symplectic, and the closeness is written here. And the almost complex structure we gave before, if you define the endomorphism, and this endomorphism satisfy the J squared equal to minus identity, this is the almost complex structure. And the V compatibility means, if you look at that, you can define the metric with respect to these two forms, and taking the J times the second vector defined with the geometric, okay? For these cases, we can say that our spaces are almost complex structure compatible with J, and for our cases, we gave this one before, JJ equal to V, this one equal, and for GVV greater than 0, we can say that the positive definite. So how can we shift this idea to Floer homology? So the Floer homology is the starting point of the actually improvement of the Morse theory, and maybe you know the Morse theory, but the Morse theory calculate the critical points of submanifold. Maybe you can see the classical example, Morse theory, the old-fashioned Morse theory. Here, for each point, if you look at that, the torus, this is the torus, and each points are the critical points, and the minimal points is one, the saddle points is one, the maximal point. So each critical points defines here the function taking the critical points to here, and inverse of the critical points define the submanifold here. And if you look at that, this point to this point, the manifolds are more or less the same. Okay, we have two holes like this, and for these two critical points, your manifold is fixed. Okay, just the the function height is changed, and that's why the result is more or less the same. But these critical points to these critical points, exactly the same manifold. And most theory try to understand that the changing between the critical points and the flow homology is the improve this theory. Actually, we can see the critical points again, but now we want to construct on this theory with the almost complex structure. Okay, so how do we structure change in these critical points? If we have the symplectic and your intersection, if you have the Lagrangian submanifolds and they transversely intersect, we can define the almost complex structure on these spaces. You can define the Novikov ring for this one. For actually AI is the intersection point of this Lagrangian. Okay, we have the Lagrangian L0 and we have another Lagrangian L1. We have two intersection point for this simple one, and Novikov rings defined that with respect to these two intersection points, we can define a ring, and for this ring it gives us the very important information. And here we try to understand the J holomorphic strip, and if you take the U, for this U is this kind of object. Okay, we want to slide your L0 to L1, and if you start with a Lagrangian submanifold, we try to find a relation between L0 and L1, and for this relation can be seen as the solution of these spaces, and du to ds and du to dt equal to 0, and this one is the J structure. So for each, actually maybe you remember the homotopy, you can slide your L0 to L1 for this theory, and here this dj bar has to be equal to 0, and for the dimension 1, actually this is nothing but the Cauchy-Riemann equation. If you check that, you can put in the complex structure also, and USI equal to LI, and so this one is the first solution, actually U0. This one is the second solution. Okay, and here for each U, if you go to the plus infinity, it's go to P. If you go to the minus infinity, you will find the Q. Okay, and here for each Lagrangian intersection, you can find the J holomorphic Whitney disk, actually. So at this point, the flow homology for the flow theory gives us that for each symplectic cases, we can find that we can shift this idea to complex plane. Okay, and here actually this construction, if you have L0, okay, this is the Lagrangian, this one is the L1. So the flow homology that sends L1 the endpoints to infinity. Okay, this is the P, this one the Q. Actually, we can pull back for all information. P sends to infinity, Q sends to infinity. So L1 is actually this one now. This is L2, and from here the Möbius transformation. Maybe you remember this strip sends to this the J holomorphic sphere. So the Lagrangian, the symplectic structure, sends to almost complex cases. Okay, and we can find the relation between symplectic idea and the almost complex idea. And the symplectic geometry and almost complex structure geometry, actually almost complex is defined in a Riemannian manifolds, and this one-to-one relation is directly related to mirror duality. So mirror duality is more or less, now we can feel the idea. Think about that the one theory for the in the string theory, maybe you remember 2A theory and 2B theory and other 5 theory. If you think about that the symplectic structure on one spaces, you can find the mirror dual of these spaces into 2D physical worlds. So calculating and mirror dual is exactly the same structure, the corresponding structure of the physical worlds. That's why the floor theory is important. So we can say that the mirror symmetry is a relation between geometric object and the Calabi-Yau. So the Calabi-Yau, actually, we have the symplectic structure, almost complex structure, everything, okay, contains. And for two Calabi-Yau manifolds, let's say M is a Calabi-Yau manifold in one special physical theory, and you can find the mirror dual of another spaces. For this theory, and we can calculate some physical information from one space to another space, but finding a mirror duals is extremely hard, and for the spatial cases are known. Theoretically, it exists, but calculating is a little bit hard. And the homological mirror symmetry conjecture is presented by the Maxim Concierge, and here the states that the derived category of coherent sheaves on Calabi-Yau manifolds, and it's equal to the Fukaya category of the mirror. So the Fukaya category is actually the induced from the symplectic cases, and the coherent sheaves, the elements of algebraic geometry. So this theory is very widespread and has to contain lots of information. And here at first you try to understand the symplecticity, and then you will construct the J holomorphic curve. A very huge theory actually, but wherever you find, wherever you catch, you can improve yourself about this theory. But theoretically, the homological mirror symmetry is the mirror symmetry conjecture is the directly physical worlds, okay, physical change, and we need two Calabi-Yau manifolds for the mirror symmetry. Actually, two means you will start one of them, you will construct the other one for the mirror symmetry, and the directly physical worlds. You remember maybe the mirror dual of two particles to itself. These particles satisfy and living in the Calabi-Yau manifold, or Calabi-Yau times the observable, right? X, which Calabi-Yau, this is the 4-dimensional, this one is the 6-dimensional Calabi-Yau manifolds, and 3 complex dimension. And if you know the Calabi-Yau case, we theoretically know that the Calabi-Yau mirror of these spaces, okay? Calabi-Yau check the mirror dual of this one, but mathematically, this is the extremely unexpected bridge between the complex and the symplectic geometry, because the symplectic geometry is different types of tools and defined with two forms, but the complex geometry defined with the Riemannian geometry, and Riemann-metric connection, loss of thing, and mirror duality gives us information, and there is the bridge, there is the relation between two different geometries. So here, lots of mathematicians studied on the mirror duality, but you know, the Calabi-Yau manifolds and Taylor manifolds is the starting at the beginning of this theory, but the theory and information induced from holonomy and lots of the recent research that can be find the mirror dual of exceptional holonomy, and the exceptional holonomy is G2 and the spin 7 geometry. Okay, and for this new direction, we can enlarge this theory into G2 and spin 7 geometry. But how can we shift this idea? Because the Calabi-Yau manifolds gives us the theory about the almost complex structure. Okay, we can shift this idea to form, Cayley form or associative form, but for the complex structure, the J, how can we shift this one? We can think about that the cross product here, the Calabi-Yau, we have J, we have Taylor form, okay, and we have metric. So how can we shift this information? J can be defined maybe the spin 7 structure with a cross product, okay? Because J sends to real parts to imaginary parts, and this is orthogonal to real part, but here we have the cross product, and the two form, Cayley form corresponds to phi, phi the Cayley form, and the G sends to G induced from the remaining metric, and at this case, can we find the same procedure into spin 7 geometry, because G2 and spin 7 is related to M theory also here. And for the G2 cases, again, some mathematician works, but Akbulut and Soler construct the Calabi-Yau manifolds in G2 because slides your dimension. G2 is a 7-dimensional object, okay? 7-dimensional object. If you reduce your space, you can find a 6-dimensional object, and that 6-dimensional object can be seen as the Calabi-Yau manifold. More specifically, they studied with if you have two plane fields on G2, and Thomas showed that directly for each G2 spaces contains two planes, okay, at the tangent spaces directly. They have the nice proof. We have the calibration, and we have oriented two fields, two plane fields. You can construct the mirror Calabi-Yau manifolds, and we wonder, can we find this one into spin 7 geometry? So again, we we try to find the two plane field in spin 7, but the difference of G2 and spin 7 in G2 directly, you have two plane field. This is the proof of the Thomas, but in the spin 7 manifold, at first you have to satisfy that the Euler characteristic of M has to 0 and signature has to divisible by 4. At that situation, you can find the two plane directly. Okay? And if you have 8-dimensional object, the Euler characteristic of if you have the 8-dimensional object, it's the spin 7 manifold. Okay? And for these spaces, if you have extra condition, Euler characteristic of M8 equal to 0, and also the signature of M8 equal to 0, modulo 4, we can say that, okay, we have two plane field on a tangent, and you have two plane fields mean two plane vector fields on these spaces. So vector space can slide on your fields, and you can define everything on the complete manifold. So vector space is very important for this information. That's why we are looking. So for this vector field, you can define the perpendicular, and for these perpendicular cases, you can use JUV, okay, almost complex structure, and this almost complex structure define the U cross V cross Z. For each point, you can define an almost complex structure. Okay? So the spin 7 manifold, if you guarantee that the two plane field, you can define the almost complex structure. Okay, this is our pocket. And for this almost complex structure, also we try to find a symplectic structure also. This symplectic structure can be defined with here the two form. This one UV, and it's two vectors. We can see that, I mean, U and V fixed, okay, because we know that the two plane exists, and these we define the complex, almost complex structure on these two places. Actually, we slide your dimension, not a complete field directly we saw. I mentioned this one before. For finding the full holonomy is the hardest case, but if you slide your dimension, you can begin at that situation, and that's why, I mean, we at first stabilize two dimension, and the rest is 6-dimensional object. You can construct a more concrete the technique, and here this omega is defined with the Cayley form. Now the Cayley form gives us the spin 7 geometry, and this JUV defined with the triple product in the spin 7 also gives us the almost complex structure. And here this almost complex structure, actually, if you apply to Z, you will find a new vector, and take the inner product of this element to V, you can directly equal to Cayley 4 form. And we prove with the SEMA for the spin 7 manifold, if you have the non-vanishing oriented two-plane field, this is the assumption of the Thomas. We can start with the two-plane field. Okay, so for this two-plane field, we can find the almost complex structure, and for this almost complex structure, who is this one? At first, we have to show that J square has to equal to identity. So for each element, you can take this. We know that the definition of these here, I forget, I missed. The elements of this one, it's nothing but phi UV, UV, ZI, and this is if you choose ZI and ZJ, arbitrary indices, if they are equal, they will find a -1, and they are different, it's equal to 0. So this is the compatible with our metric. Okay. We showed that this J is minus identity. We satisfy the almost complex structure. And what did I do about this part? The mirror duality of spin 7 manifolds. Actually, I wonder that can we find the Calabi-Yau manifold in spin 7 structure? I started with the four plane. Okay, so again the same thing. Can we find the four plane, four different vector fields sliding on your spaces or defined on your spaces, and the Kadek and the Vanzura show that if the V6 means, we mentioned before, the Stiefel-Pitney class equal to 0, the Euler class of M equal to 0, and the complete definition, actually, this T square M equal to this one, the very complete definition, or very complete information about the finding four vector fields. If all of them satisfy, we can say that M has four linearly independent vector fields. But the special case, I said that if you are living in a spin 7 manifold, if you are inside of a spin 7 manifold, only V6 equal to 0, we can say that we have four linearly independent vector fields. Now, we are living in an 8-dimensional object, and V6 equal to 0, we can say that four linearly independent vector fields. And for these four vector fields, we know from the study of mine and Salur, we have Calabi-Yau manifold from the 2-dimensional plane, and if I study it with the four vector fields, you can separate into two pieces, and this gives us the two different mirror dual, U, V, Y, and W for vector field, and we can define the two different Calabi-Yau manifolds, and they are mirror dual to each other. But this one is actually how do we construct this one? For UV, we can use the triple product, and YW, we can use the triple product also. Okay, and this is the interior product. Reduce your the form dimension to 1 degree lower. This is 4-dimensional object. This one is the interior product. So the IV phi is the 3 form, and IU 3-dimensional form induced to 2-dimensional form. Okay, so for these 2-dimensional form can be seen as the symplectic form, and the real of omega can be seen. This is 4-dimensional. So this is 4 form. We know the U as a vector field. You can reduce your dimension with this U. You will find the 3-dimensional object. Okay, this 3-dimensional object, and this one is 3 form. This one is 2 form. So from here you can construct Calabi-Yau manifolds, and they compare satisfy the same induced from the same form. You can find the Calabi-Yau mirror dual of these spaces. So what did we do? We start with the spin 7 manifold. We know that for the two-plane vector, with the two-plane vector fields, we can construct the Calabi-Yau manifold. Now we wonder that if you have the 4-vector field, you can separate them into two pieces. We have two different Calabi-Yau manifolds and mirror dual to each other. The direct equivalent idea of the Calabi-Yau manifolds and the Floer techniques and the mirror duality in the homological mirror duality idea. Okay? But again, the bigger question for finding the mirror duality in the Calabi-Yau manifolds is still the open problem. you can look at that. Those kinds of work a little bit complicated. You can check. My idea and my studies is a little bit generalization of Akbulut and Saluk for the G2 cases into spin 7. I started with the two vector fields. I wonder that can we find the mirror dual into 4-dimensional vector field, and I can find two different Calabi-Yau manifolds. The R8 is the simple example, but we can generalize this idea into higher complicated example, but still I'm studying on this theory. Okay? And this is the end of the lecture series, and the collaborated geometry article is magnificent. The article, you can check them. Everything starts with these papers, and I used many different articles, but my theory is the generalization of this one, mirror duality via G2 and spin 7 manifolds, and you can check other papers, and we can you can write an email about this topic. You can look at another paper. And thank you so much for your patience. If you have any question, we can talk. And there are lots of open problems in this theory, and very new branch of geometry. You can look at that mirror duality also. And thank you so much.
Oh, thank you very much. Nice results. Any question? All right, so we can finish this one.